This is Babitha, working as Assistant Professor in the Department of ECE at Institute of Aeronautical Engineering. In this session, I'm going to discuss about Darlington Amplifier as well as Cascode Amplifier. So while coming to the contents, just I'll give brief revision related to the multistage amplifier. Why? Because this Darlington Amplifier as well as Cascode Amplifiers are the one of the types of multistage amplifiers here. And next we are going to discuss about the Darlington Amplifier, then Cascode Amplifier. So before going to the Darlington Amplifier and Cascode Amplifier, just we'll see about the multistage amplifier here. So here what is meant by multistage amplifier? If we take a similar type of single stage amplifiers and if we interconnect that single stage amplifiers using some coupling elements, that coupling elements may be resistors or capacitors or transformers. By using any coupling element, we can able to interconnect the single individual stages to make it as multi-stage amplifier. And the process of interconnecting output of one stage to the input of the next stage is nothing but cascading of the amplifiers. And in the multi-stage amplifiers, we are using the direct coupling or RC coupling or transformer coupling here. Among the three types of coupling, we can utilize any one of the coupling scheme in order to make it as a multi-stage amplifier from the individual single stage amplifiers. Actually, why we are moving for this multi-stage amplifiers means in order to improve the overall voltage gain as well as current gain as well as input impedance of the amplifier circuit, and in order to reduce the output impedance of the amplifier circuit. Why again we are improving these parameters means in some applications the parameters providing from the single stage amplifiers are not sufficient. That parameters are not drive the high power applications. So in order to utilize high power applications, we are making the multi-stage amplifiers here. So this is a circuit for the multi-stage amplifier. Here we are taking first stage, that is the single stage amplifier, and one more stage as the second stage we are taking, and the gain provided by the first stage we are taking here it as AV1, that is voltage gain of the first stage, and the gain provided by the second stage we are taking here it as AV2. And here the coupling element we can use it as either resistor, capacitor combination or else transformer. Okay, the coupling element may be either combination of resistor and capacitor or else transformer. So if we see the overall voltage gain of this two-stage multi-stage amplifier, that is AV equal to AV1 into AV2. So the overall voltage gain is the product of the voltage gains of individual stages here. So if you take the only single stage amplifier, we may get the gain as either AV1 or AV2 only. But if we take the two-stage or multi-stage amplifier, here we can able to improve the overall gain of the system. So because of that reason, we are moving for the multi-stage amplifier. So in the multi-stage amplifier, in the previous sessions, we have already discussed about direct couple amplifier and resistor capacitor coupling amplifier and transformer coupled amplifier. So in order to overcome the disadvantage of the RC coupled amplifier, we moved for the transformer coupled amplifier. So what is the basic drawback of RC coupled amplifier here? It is effective load resistance. That is nothing but the input impedance of the second stage or the high input impedance of the second stage is providing the loading effect to the output impedance of the first stage. So because of that reason, the overall impedance is reducing, the effective load for the final stage is increasing. So because of that reason, the overall gain of the system is reducing here. So the purpose of the multi-stage amplifier here is to improve the gain, but because of that RC coupling, the gain value is reducing. So that's why in order to overcome that, again we went for the transformer coupling. So transformer coupling will rectify the problem of effective load resistance, and it provides better impedance matching between the stages, whatever we are interconnecting in the multi-stage amplifier. So those and all we discussed in the previous session. So along with the RC coupled amplifier and transformer coupled amplifier, we are having two more multi-stage amplifiers. Those are Darlington Pair or Darlington Amplifier and Cascode Amplifier. So now we'll see about the Darlington Pair. So what is mean by this Darlington Pair? Why we are moving for this? So generally, if we take this single stage common emitter amplifier or common base, common collector, any one configuration amplifier, they may provide the gain levels to some extent as well as input output impedance levels to some extent. But if you want to improve more current gain and more input impedance, then we can move for this Darlington pair. So in the case of Darlington pair, we will interconnect two similar type of bipolar junction transistors. Okay, we will interconnect two similar types of bipolar junction transistors. So here I told that the overall current gain is improving in the case of Darlington pair. How it is improving here means it consists of two bipolar transistors. Those are interconnected in such a way that the current amplified by the first transistor is again amplified in the second stage or second transistor. So the overall gain is equal to the two individual gains multiplied together. So we will get the overall gain of Darlington pair, that is HFE, is equal to the forward current gain of first transistor into the forward current gain of second transistor. So finally we can say this Darlington transistor gives much high current gain compared to the single bipolar junction transistor. So from this Darlington pair we can able to improve the overall current gain as well as overall input impedance of the amplifier stage, and the output impedance we will reduce here. So these are the basic requirement for any amplifier circuit. So in the case of Darlington pair, so here we are using two transistors. This is first transistor and this is second transistor. We are interconnecting in such a way in order to deliver high current gain from a low base current here. By providing very less base current, we are able to get the high current gain from this Darlington amplifier. So in this particular configuration, the emitter terminal of the first transistor is connected to the base terminal of the second transistor, and the collector terminals of both the transistors are tied together. Here, the collector of first transistor and the collector of second transistor are tied together, and we can take it as single collector. Okay, and also the emitter terminal of the first transistor and the base terminal of the second transistor are tied together, and the emitter terminal of the second transistor we are taking it as the emitter, and the base terminal of the first transistor we are taking it as the base. So if we interconnect like this, if we tie both the collector terminals together and the emitter terminal of the first stage to the base terminal of the next stage, so that it becomes a single transistor with very high current gain, that we can represent in this way. This is the Darlington pair, whatever we discussed in the previous slide. So this one we can represent it as single transistor. Why? Because it is also having the combination of these two transistors are also having three terminals only. Here it is collector, emitter and base terminals. So equivalently we can replace it as the single transistor with collector, base and emitter terminals. So here the current gain provided by the first transistor is beta 1 and the current gain provided by the second transistor is beta 2. So the overall current gain I am taking here as beta, that is equal to beta 1 into beta 2. So for this transistor overall current gain is beta. So this particular kind of Darlington Pair transistor is also called as high beta transistor. Why? Because it is providing very high gain compared to the individual amplifier stages. And because of this connection, the overall input impedance is also improving more. So till now we discussed about the Darlington pair and how to form the Darlington pair. So this Darlington pair is also called as Darlington emitter follower circuit. Why? Because the second stage of the transistor is following the emitter terminal here. Why? Because the emitter terminal of the first transistor is connected to the base terminal of the second transistor. Because of that reason, Darlington pair is also called as Darlington emitter follower circuit. So this is the circuit we have discussed till now. This is the Darlington pair. So if we provide the input signal to this Darlington pair as well as if we take the output across the second stage so that it becomes the multistage amplifier. So for that purpose, we are providing the input signal Vs, that is sinusoidal signal with some frequency and amplitude. We are providing through the source resistance Rs to the base of the first transistor. So because of this voltage through the source resistance Rs, the current Ib1 which is flowing through the base terminal of the first transistor, and the input voltage developed across this first transistor we are taking here it as Vi here, and the output current of this transistor we have taken here it as IE1. The first transistor output current is IE1. So that IE1 current we are connecting directly to the base terminal of the second transistor. So that's why always in this particular configuration, the emitter current of first stage is equivalent to base current of the second stage. So that's why IE1 is equal to IB2. And here the emitter resistor RE1 is also providing here, and it is providing infinite impedance. And while coming to the second stage, for the second stage input we are providing from the emitter of the first stage, and the output we are taking across the emitter terminal or across the emitter resistor of the second stage. So that is IE2. So for both the collector terminals we are providing the supply voltage VCC. So this is the Darlington pair construction after providing the input signal as well as after taking the output across the emitter resistor. So now we have to analyze this particular circuit here. So in the case of single stage amplifier, to do the analysis, first of all we have to remove the supply voltages as well as any capacitors which are present in the circuit. We have to short that, and we have to replace the transistor with its hybrid equivalent circuit. But in the case of multi-stage amplifier, how many stages are there? That many number of times we have to do the analysis. Here in this particular circuit we are having two stages, so we have to do the analysis for the first stage as well as for the second stage. And so in order to analyze the circuit, we have to replace the transistor in its hybrid equivalent model. So in this hybrid equivalent model, we are having the exact analysis as well as approximate analysis. So when we need to go for the exact analysis and when we need to go for the approximate analysis. So if the load resistance value as well as output admittance of the amplifier value, the multiplication of the two values are less than 1 means we have to go with the approximate analysis. If this value is not satisfying, this particular condition is not satisfying means then we need to go with the exact analysis of the hybrid circuit. So in the case of exact analysis, we will take all the parameters, that is input impedance, forward current gain, reverse voltage gain and output admittance. All the parameters we are going to consider to do the analysis in the exact model. But in the case of approximate model, we can able to neglect the HOE as well as HRE values. After neglecting this, in the simplified hybrid circuit, we are having HIE and HFE only. So in the input circuit, we will include the input impedance, and in the output circuit, we will include the forward current gain in the case of approximate model. So in the Darlington pair, for the second stage, we are taking the approximate analysis, and for the first stage, we are going with the exact analysis. Why for the first stage we are going for the exact analysis means, in the first stage, the the input impedance of the second stage acts like a output impedance for the first stage. So the input impedance is very high here, so that in that way the output impedance for the first stage is also very high. So that's why once that resistance is very high means we cannot satisfy this particular condition in the first stage. So that's why for the first stage we are making the for the first stage we are making the exact analysis, and for the second stage we are going to perform the approximate analysis. So this is the hybrid equivalent circuit of the second stage, and this is the hybrid equivalent circuit of the first stage. So now we are going to analyze this particular second stage analysis. Always in the multi-stage amplifier, first we have to do the analysis for the second stage and then for the first stage. So while coming to the analysis of second stage, for that I am taking the second stage equivalent circuit. So to find the overall current gain of this second stage, that is the output current divided by input current here. So in this case, the output current is I0, that is flowing through the emitter resistor RE. But actually, the current flowing through the transistor is emitter current, and that is opposite direction to this I0. So that's why I0 I am replacing here with IE, and the base current and the input current is as it is. So we have to find the value of this one I0 by IB to find the overall current gain of the second stage. So that is minus IE by IB. So here IE is nothing but the sum of the current which are coming from the base terminal as well as collector terminal. So that's why here it is IB plus current through the collector terminal is HFE into IB. So that's why IB plus HFE into IB is the total emitter current. So divided by the base current or input current is IB. And if we take IB common from this, we will get it as IB into 1 plus HFE by IB. So these IB will get cancelled. So the current gain of second stage is 1 plus HFE. And similarly, we need to find the input impedance. So input impedance is nothing but ratio of input voltage by input current here. So from the input side, we can able to find this value. So for that, we have to apply the Kirchhoff's voltage law to the outside loop of this particular circuit. That is V2, the voltage which is flowing in the circuit, minus IB2 into HIE, the drop across the HIE resistor, that is minus IB2 into HIE, minus drop across RE resistance, that is minus I0 into R. So here we are applying the KVL. We should not consider this particular current gain term here. So only the voltage drops in the circuit we need to consider. So that's why it is V2 minus drop across HIE and drop across RE, that is equal to 0. And from this V2 equal to, we can send these terms into right side, IB to HIE plus I0 R. So from this equation, we can write V2 equal to, if we take IB2 common, we will get it as HIE plus I0 by IB2 into R. So this IB2, if we take left side, we will get it as V2 by IB2 is equal to HIE plus I0 by IB2 into R. So here V2 by IB2 is nothing but input impedance or input resistance, that is equal to HIE plus, and again I0 by IB2 is nothing but here current gain of the second stage. So we can replace this term with AI2. So HIE plus AI2 into RE. So the overall input impedance is HIE plus, again AI2 value just now we have calculated, we got it as 1 plus HFE. So after substituting this AI2 value in this equation, this is the final input impedance of the second stage. So RI2 equal to 1 plus HFE into R. Why we are approximating in this way means this input impedance of the second stage is less than the 1 plus HFE into RE term. So that's why we are neglecting the term HIE here. So this is the final input impedance of the second stage here. And next we have to analyze the first stage. So till now we have analyzed the second stage and we have calculated the current gain as well as input impedance provided by the second stage. And in the first stage we are going for the exact analysis, I have already mentioned. Why? Because the input impedance of the second stage acts like a output impedance for the first stage. So the input impedance of the second stage, that is RA2, is very high value. Okay, so in this case, if we perform or if you multiply HOE into RA2, it should not satisfy this particular condition. So that's why we are going for the exact analysis instead of approximate analysis. So this is the H parameter equivalent circuit of the first stage. So though it is exact analysis, we have to include all the H parameters, that is HIE, HRE, HFEI, HO. And along with this, we need to include all the voltages as well as current which are flowing in the first stage. So the input current is the IB1 and the input voltage is VBE1 and the output voltage is VCE1. Here we have already mentioned. And the output current is emitter current IE1. So this is the first stage, and from here again it will be second stage. And next we are converting this CC configured parameter into CE configuration. Why? Because the second stage already it was common emitter configuration. If the first stage is also in the common emitter configuration, means directly we can perform the multiplication operation in order to get the overall values. If we are taking the different configured transistors, means we cannot able to find the overall voltage gain as well as input impedance directly here. So for that purpose, we are converting the common collector to common emitter here. So this is the conversion circuit here. So if we compare this circuit with the previous circuit, HIE is again HIE only, but HRE VCE is shifted to here and collector is grounded here, and HFE IB is, that current direction is from collector to emitter, and the output parameter is HOE. So to find all the H parameters here, first H parameter is H11, that is nothing but input voltage by input current when the output terminals are short circuited. So that in the common emitter configuration, we can represent it here as HIE equal to VBE by IB when VC equal to 0. So to satisfy this particular condition in this circuit, we should make VC equal to 0. So once VC equal to 0 means this resistor is also short circuited here. So if we apply KVL for this circuit now, we will get it as VBE, this voltage minus drop across this resistance, that is HIE. Sorry. HRE VCE equal to IB HIE. So these three drops we are taking into consideration here. Why? Because these and all are short circuited. Once the output terminals are short circuited means what are the elements which are connected to that also short circuited here. So here VC equal to 0. So this total term is 0. So once this total term is 0 means we will get it as VB equal to IB HI. So from this we can write VBE by IB equal to HIC, and that is equal to HI. So that is nothing but in the common collector as well as in the common emitter configuration, the input impedance is same. So that's why we are replacing HIC with HIE directly. So that's why in the equivalent circuit directly we indicated with HIE only. And next parameter is H21, that is current gain, forward current gain, I2 by I1 when V2 equal to 0. So this is the case for the normal hybrid equivalent circuit, but for the common emitter configuration, the output current is emitter current and the input current is base current, and output voltage is VCE, that should be equal to 0. So here we require the current again, so that's why we are applying the Kirchhoff's current law to the same equivalent circuit. So if you apply KCL to this circuit, we will get it as this current IB plus this current again HFE IB plus emitter current IE, that is equal to 0. And here if we take IB common and if we send it to the left side, we will get it as minus of 1 plus HFE, that is equal to HFC. So HFC is nothing but minus 1 plus HFE in the case of common emitter configuration. See, in the common emitter configuration it is HFE, but in the common collector it is minus of 1 plus HFE. So when we are converting from CC to CE, we have to replace HFE with minus of 1 plus HFE. And next parameter is H12, that is forward voltage, reverse voltage gain V1 by V2, that is when the input terminal are open circuited. So in this case HRC is equal to VBC, that is input voltage, divided by VCE, that is output voltage when the base current is 0. So to find the VBC voltage base to collector voltage, we have to take it as VBE, this voltage, as well as VEC, this voltage. If we add these two divided by VEC will give the overall reverse voltage gain. And here in this case the base current is 0. So once the base current is 0 means VBE equal to HRE VC, and that is equal to minus HRE VC. So HRC we can write it as 1 minus HRE. In the common emitter it is HRE only, but in the common collector it is 1 minus HRE. And the last parameter here it is output admittance, that is output current by output voltage when the input terminals are open circuited. So that is nothing but HOC equal to IE by VEC when base current is equal to 0. So when IB equal to 0 here means we will get VEC is equal to the current IE into 1 by HO. So here IE by VEC is nothing but HOE, that is equal to HOC. So this is the equivalent circuit after doing the analysis of first stage as well as second stage. See here, this one is the first stage. Still here it is the first stage. And after this, it one is the second stage. So now we have to analyze this equivalent circuit with the combination of first stage and second stage to get the overall parameters of the Darlington pair. So the current again after converting it into the CC configuration, Again, we need to find the parameters of the first stage. So the current gain here it is IB2 by IB1. Okay, IB2 is the current which is flowing to the second stage base, and IB1 is the input current of the first stage. So AI1 equal to, here IB2 is nothing but IE1. We have equated while designing the circuit itself, we have equated IE1 equal to IB2 here. So that's why IB2 equal to minus IE1 divided by IB1. So what is our emitter current I1? That is the sum of the base current V1 IB1 plus IC1. So IC1 from the circuit here it is HFE IB1 plus HOE VC1. So this is the total collector current in the first stage. And here VC1 is nothing but VCE1 is nothing but minus IB2 into RL1. So after substituting that, we will get it as HFE IB1 plus HOE IE1 into RL1. And substitute the value of this collector current I1 in the IE1 equation to find the current gain. So if we substitute that, we will get it as IE1 equal to minus IB1 minus of IB1 plus, this is the collector current value, total value we have substituted here. So after multiplying it with minus, we will get it as minus IB1 minus HFE IB1 minus HOE IE1 into RL1. So I am taking these terms to the left side, that is HOE IE1 RL1 I have taken to the left side. I will get it as, and if we take minus IB1 as common here, we will get it as 1 plus HOE. So minus IE1 by IB1 equal to 1 plus HFE by 1 plus HOE into RL. So this is the overall current gain of the first stage. And next, to find the final current gain, we know the value of RL1, that is 1 plus HFE into RE. So after substituting that value, we will get it as this much. And here the forward current gain HFE value is far greater than 1. So that's why in the numerator as well as in the denominator, we are keeping it as 1 plus HFE by 1 plus HOE into HFE into RE. So in this term, we have neglected the 1 by, because forward current gain is far greater than unity value. So this is the output impedance of the first stage. And next, to find the input resistance, that is Vi by IB1. For that, apply KVL to the output loop. We will get it as Vi, the input voltage, IB1 HIE, the drop across this particular resistor, and minus HRE VC1 and minus VC, even all the voltages in the circuit. And all these terms we are taking back to the right side, all these terms, so that we will get it as this much. So here in this particular equation, this HRE VCE term is very less, so that we can neglect that. Why? Because this value is 2.5 into 10 power minus 4. That is very, very less value, so that we can neglect that particular value in the equation. After neglecting HRE VC1, we will get it as IB1 HIE minus of minus VC1 is nothing but again IB2 into RL. So IB1 HIE minus of minus is plus IB2 into RL. And in this, if we take VI by IB1, that is nothing but take IB1 common here. If we take IB1 common, we will get it as HIE plus IB2 by IB1 into RL. So now this IB1 we are taking into the left side, so that we will get it as HIE plus IB2 by IB1 into RL. And again this IB2 by IB1 is nothing but the current gain of the first stage. So that's why we replaced it with AI1. So the overall input impedance of the first stage is HIE plus AI1, and again RL1 value is 1 plus HFE into R. and again substitute the value of AI1, this one, that is 1 plus HFE. So HIE plus, this is the AI1 value, 1 plus HFE, and again 1 plus HFE into RE divided by 1 plus HOE HFE RE. So here these two are same. So we written it as whole square 1 plus HFE whole square divided by overall denominator as it is. And we can approximate here it as these value only. Why? Because if we compare these two terms, HIE value is very less. So that we can neglect this HIE value here. So after neglecting HIE value, the overall input impedance of the first stage is 1 plus HFE whole square into RE by 1 plus HOE into HFE into RE. So till now we have seen we have find the parameters in the first stage as well as in the second stage. So to find the overall voltage gain as well as overall input impedance, we have to multiply the gains of individual stages. So the overall current gain I am taking here it as AI. That is the multiplication of the current gain in the first stage and the second stage. So first stage current gain we got it as 1 plus HFE by 1 plus HOE into 1 plus HFE into RE. And the second stage current gain is 1 plus HFE. So again it is 1 plus HFE whole square divided by 1 plus HOE into 1 plus HFE into RE. So this is the final overall current gain of the Darlington pair. So the purpose of the Darlington pair here is to improve the overall current gain as well as input impedance of the system. So now we will compare whether that particular parameters are improved or not. So for that purpose, input impedance as well as current gain we are taking for the single stage amplifier as well as for the Darlington amplifier. So in the case of single stage common emitter amplifier, the input impedance is 1 plus HFE into RE. We will get it as almost 168.3 kilo ohms. But in the case of Darlington amplifier, it is improved from kilo ohms to mega ohms. That is 1.65 mega ohms. And while coming to the current gain, for the normal transistor, it is 1 plus HFE, that is 51. But in the case of Darlington amplifier, it is improved from 51 to 500. So if we see these parameters from this analysis, we can say from the Darlington amplifier, we can improve the overall current gain as well as input impedance of the system. So wherever the applications require the high current gain and high input impedance, we can utilize this Darlington pair or Darlington amplifier. So while coming to the advantages of this Darlington pair, first thing is it provides very high current gain, just now we have seen, and also very high input impedance. And these are available in single package. Instead of interconnecting two separate transistors, we can get it in single transistor. And it is very high. It is we can easily construct this particular circuit, and it is very simple. While coming to the disadvantages, the switching speed is very low here. Why? Because the input of the first stage is depending upon the output of the first stage. So to get the second amplifier output, it should wait for the output of the first stage. So that's why the speed is reducing here. And the bandwidth also less here, and it takes very high base emitter voltage in order to provide high current gain V2. And the saturation voltage level is also very high. So once the saturation voltage level is very high, means the power dissipation also very high in the circuit. That is the drawback of the Darlington amplifier. Even though it is providing the high current gain and high input impedance, but it is providing high dissipation also. And while coming to the applications of the Darlington amplifier, we can utilize for the power regulation. And in the audio amplifiers, we can use it as output stage. Why? Because it is providing very high gain. And in the display drivers, to display the values, we can use it. And in the motor controllers, and the touch and light sensors, and in the solenoid control circuits, we can able to utilize this Darlington amplifier circuit. So next type of multi-stage amplifier is the Cascode Amplifier. In the case of Darlington Amplifier, we improve the current gain as well as input impedance of the circuit. And we can also improve the overall voltage gain as well as overall input impedance of the circuit by using this Cascode Amplifier. So in the Cascode Amplifier, we will use the common emitter as well as common base configuration transistors here. If we interconnect the two transistors, we can able to improve the overall voltage gain as well as input impedance of the circuit. So this is the circuit for the Cascode Amplifier. So in this case, the first stage is the common base amplifier and the second stage is the common emitter amplifier. So here these R1, R2 resistors are providing the proper biasing required for the transistor T2, and this R3 and R4 are providing the proper biasing and stabilization required for the transistor T1. And we are applying the input signal as a sinusoidal signal with some frequency and amplitude through the source resistance Rs and through the coupling capacitor C1. So the function of the C1 is to pass the AC signal to the base of the first stage and it blocks the DC signal to the first stage. So once we provide the input for this base of the first transistor and we are operating this transistor in the active region. So to make it as active region, we have to apply forward bias to base to emitter junction and reverse bias to collector to base junction. And also it should provide the proper operating point. So we are operating the transistor T1 in that particular condition, and along with that we are applying the input voltage Vs. So now it will amplify that applied input voltage Vs and it will give it to the common base transistor. Why? Because the emitter of this one is interconnected to the collector of this one. So the overall output voltage we will take it across the second stage, that is T2 stage, and across load resistance Ra. And this Re1 is nothing but the emitter bypass resistor and C3 is the emitter bypass capacitor. It will provide the path for the amplified signal. Again, we need to analyze this particular Cascode amplifier. Again, for the first stage as well as second stage, we have to perform the analysis individually. Then we have to take the overall voltage gain as well as current gain and input impedance. So why we are moving for this Cascode amplifier? Actually, here it is means in the common base circuit, if you take single common base circuit, it will provide very low input impedance. Common base circuit will provide very low input impedance. But if you take the Cascode amplifier, it will provide the high input impedance. Why it is providing high input impedance means we are interconnecting the common base with the common emitter. This particular common emitter amplifier will provide high input impedance. So because of interconnecting these two, so the overall input impedance is improving as well as the common emitter amplifier also provides the high voltage gain. So both the voltage gain as well as input impedance are improving when we interconnect common base as well as common emitter amplifiers. And this Cascode amplifier will provide the performance for the high frequency signals. So this is the AC equivalent circuit of this Cascode amplifier. So to get the AC equivalent circuit, we have to short all DC sources, that is VCC, and we have to short this capacitor C1, C3 also. After shorting that, we will get it as the AC equivalent circuit. See, here supply voltage is short means that interconnected resistors are also shorted here. So that's why RL is shorting here, and C3 is short circuited means along with that RE1 is also short circuited. C1 is short circuited means along with that R1, R2 resistors as well as R3, R4 resistors are also short circuited. So the remaining components, whatever present after applying DC, short circuited, and capacitors are also short circuited. So this is the equivalent circuit, and it consists of the source resistance and RB resistance. RB resistance, here it is the parallel combination of R1 and R2, and load resistance RL that is connected to the second stage. This is the stage 1 T1, this is stage 2 T2. So this is the H parameter equivalent circuit of this one. Both the transistors are replaced with the hybrid equivalent models. That is nothing but this is CE configuration till here. That is first stage. That is CE. And the second stage is this one. That is CB configuration. So in order to analyze this particular circuit, I am assuming some values to the resistors which are present in the circuit. That is RS, I am taking here it as 1 kilo ohm, R3 resistance 200 kilo ohms, R4 resistance 10 kilo ohms, and the load resistance is 3 kilo ohms. And transistor hybrid parameters for both the configurations are same here. That is HI is 1.1K and HFE is 50 here. Why we are mentioning only 2 H parameters among 4 H parameters means in both the first stage as well as in the second stage we have considered the approximate analysis, not the exact analysis. So in the approximate analysis only we are having the HIE as well as HFE parameters only. So that's why in the first stage as well as in the second stage we are having only HIE and HFE parameters along with all the input output voltages and input output currents. So first I am taking the second stage, that is common base configuration. So for the common base configuration, current gain is HFE by 1 plus HFE. So the analysis of all the configured amplifiers we discussed already in the previous sessions. So from that only we have taken these formulas. HFE by 1 plus HFE. HFE value we have taken here it as 50. So after substituting that, we will get it as 0.98. And the input resistance is HIE by 1 plus HIE. So input impedance we have taken here it as 1.1K. So after substituting that, we will get it as 21.56. And the voltage gain is equal to current gain into load resistance by input resistance. So the current gain value we have calculated already, that is 0.98, and RL2 is 3 kilo ohm and RA2 is 21.56. After substituting all these values, the overall voltage gain is 136.36 for the common base stage. And similarly, analysis of the first stage, that is common emitter amplifier. So in the common emitter amplifier, the current gain is minus HFE. Minus indicates the output is 180 degrees phase shift with the input in the case of common emitter amplifier. So that's why the gain is in negative form, minus 50. And the input impedance is directly equal to the input impedance of the hybrid equivalent circuit, that is HIE, equal to 1.1 kilo ohm. And the voltage gain of the first stage is current gain of the first stage into RL1, the load resistance divided by input resistance. So already we have calculated the current gain of the first stage, that is minus 50, and the load resistance value is 21.56 and the input impedance is 1.1K, and this value is minus 0.98. So both the current gain as well as voltage gain are 180 degrees out of phase with the input signal in the case of common emitter amplifier. And this negative sign is applicable for odd number of stages, and if you take even number of stages, you will get it as positive only. So now we have to find the overall parameters. So the overall voltage gain is the voltage gain of the first stage multiplied with the voltage gain of the second stage. So first stage voltage gain we got it as minus 0.98, and the second stage voltage gain is 136.36. So the overall voltage gain is minus 133.63. And the input resistance here it is nothing but input impedance of the first stage parallel with the potential divider network. So Ri1, so here Rb is nothing but R3 parallel with R4. So that's why here we are taking Ri1 parallel with R3 parallel with R4. After substituting all the values, we will get it as 986.1. And the overall voltage gain, by considering source resistance into consideration, in that case we will get it as minus 66.35. And the overall current gain after including the source resistance into consideration, we will get it as minus 43.9 here. And to find the output resistance of the first stage is infinity, and as well as second stage is also infinity. But overall output impedance is the parallel combination of the output resistance of the transistor as well as load resistance. So here output impedance is infinity, but the load resistance is 3K. So if we take the parallel combination of two resistance values, means which resistor is having low value, that we will get it as output. So R0 is 3 kilo ohms. So this is the analysis part of the Cascode amplifier. From this analysis, we can see the overall voltage gain as well as overall input impedance of these values are increasing compared to single stage amplifiers. Well, coming to the advantages of Cascode amplifier, it is providing high input impedance, high output impedance as well as high voltage gain. And disadvantage here it is. So here we are using two transistors, so that we require very high amount of voltage supply, and sufficient amount of drain to source voltage must be provided to both the transistors. So because of that, there is a limit in the supply voltage because of interconnection of two stages. And while coming to the applications, we can use it for the tuning purpose in the TVs. In order to make the channel change, we can use tuning. In that purpose we can use that. And amplitude modulation techniques, also we can utilize this cascode amplification. So amplitude modulation means whatever the input signal we wanted to send it from a transmitter to receiver, that message signal according to the carrier signal, we will change the amplitude of the shape of that signal according to the carrier signal. So in that particular process, we will utilize this cascoding technique. Why require that particular cascode technique here means, if the particular circuit is having high voltage gain only, it can able to perform the modulation or amplitude modulation here. So because of that reason, we are including the cascode amplifier in the amplitude modulation scheme. So in this session, we discussed about the Darlington amplifier as well as Cascode amplifier. In that, we discussed the construction and operation of both the multistage amplifiers, and also we have seen the analysis part of both the multistage amplifiers along with its advantages, disadvantages, and applications. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.